first term, the n's simplify, so we have p times n plus 1 over 2, which remains. And here we have 1 minus p times the summation of I from 1 to n, and that's going to be n times n plus 1 over 2, and the two n's cancel, so you get n plus 1 over 2 left. Okay. How do we change? Notice that the index of the second term goes from I plus 1 to 2n, and then we change it to 1 to n. We change that, right? How do we change it? Well, basically, let's find out what's going on here. So the 1 minus p over n, that's no problem at all, because that's just the probability coming out in front of the summation. So now, what happens when I is equal to I plus 1? When it goes to I plus 1, then we have I plus 1 minus n. So, and when I is equal to 1 to n, then this is equal to 1. So basically our, oh sorry, okay, so this is the mistake here. That's what should this be? That's the problem. This is just a typo. So I goes from, same as here, n plus 1 to n. So when I, the lowest value in the second summation is n plus 1. How much is n plus 1 minus n? 1. So therefore this is just 1. So therefore, notice that this is when I is 1, it's 1. How about when I goes to I plus 2? I plus 2, n plus 2 rather. N plus 2 minus n is 2, so when I is 2, this is just 2. At the very end, the value of I goes to 2n. 2n minus n is n, so when I is the maximum value n, this is just n. So we simply change the summation. How do we do it? Well, basically what we did was we had n plus 1 as the bottom index, so we subtracted n from here. So we subtracted n from here, we had to add n into the summation term, which we call the summand. So if we decrease the index by n, we have to increase the usage of the index by the same amount to balance out. And ultimately, this summation here, as long as we understand this is n, and this summation here are exactly the same. Is that thing being recorded the whole time?
Yeah.
Okay, fine. Okay, so after we have this, notice that we have p times this, 1 minus p times this. So essentially, when you do the algebra, it comes out to n plus 1 over 2. So we have two results. One is the previous result, which is when we have unordered, and then we have this one when we have ordered. The question becomes, when is this second version of the algorithm better than the first version of the algorithm? And the answer is going to be as follows. An algorithm is better than another algorithm if its instruction count or its time complexity is lower than another. So therefore, the unordered search, and this is the early stop. Early stop is the second version. So notice that that's actually the algebraic expression for the added complexity of the unordered search. This is the algebraic complexity of the early stop, which is the second one. We stop early because we can accept, we can find early, and we can reject early. That is not going to be there. So therefore, we force the condition of unordered greater than early stop. So this is the condition where early stop is better than unordered. And that creates a relationship, or a relation. And so what we need to do is we need to solve this algebra here. How do you stop this relationship? Well, so this is greater than this one, that means this is better. Because if it's less than, it's better. That's algorithmically speaking. So therefore now we substitute the algebra here and the algebra here, and now all we have to do is just basically try to combine these using our algebra. So you can see that here, this is over 2, so I put this also over 2 by multiplying by 2 over 2, and that gives me 2n times 1 minus p over 2. Okay? Then this one is fine, just leave it the way it is. Then I multiply stuff out in here, and I get all this stuff over 2 is greater than n plus 1 over 2. Then I combine, I have Pn minus 2Pn is going to be minus Pn. I have P plus 2n stays. And then I have a 2 on the bottom here, I have a 2 on the bottom here, so I can multiply both sides by 2. So now that gets rid of the denominator, so I have this expression here. Okay, now I'm going to do some more algebra, so I'm going to get P minus Pn. I'm going to subtract 2n from both sides. So 2n, n minus 2n is minus n, so I get 1 minus n on this side. Now I can factor this, take a p out of this, it's going to be p times 1 minus n is greater than 1 minus n. I'm almost done, but I have to be ultra careful here, because basically now what I'm going to do is I'm going to see, notice that basically both of the sides have a 1 minus n. I'm going to divide by 1 minus n. But this is an inequality. And because it's an inequality, dividing by a negative value will switch the inequality from greater than to less than, from less than to greater than, from greater than or equal to less than or equal to, etc. Now, I know that dividing by 1 minus n is negative. How do I know that? Because 1 minus n is assumed to be a large value for the algorithm. So therefore, 1 minus n is definitely, for large values of n, is going to be negative. Which is fine. We can divide, but when we divide, what happens is the 1 minus n cancels and we get p. 1 minus n cancels with the same. We get 1, but the operator goes from greater than to less than. So this is the result of the question, when is the second version less than or better algorithm than the first version? On average. That's an important result, because on average is reasonably how it's going to behave in real life, right? So the answer is the second algorithm version is better whenever p is less than 1. Well, first of all, p is a probability, and the value of probability cannot be less than 0 and cannot be more than 1. So therefore, the only value for probability which is not less than 1 is when p is exactly 1. And that's when p is 1. And that means that the probability of finding the element in the array is 100% certain. So we now have to interpret our algebra. The interpretation says the second algorithm is better whenever the probability of finding the element in the array is less than certain. So if the probability is not 100% all the time, then the second version will tend to be better, on average. Okay? Now, I could have asked a totally different question. I could have said, when is this algorithm worse? So to do that, I would take the algebra result of this algorithm and put, instead of less than on this side, I would flip this operator. Because I would say, when is this one worse, making this one better? When is this one better? So what would happen is, if I start with my operator switching from here to here, from this one to this one, then everything will actually proceed exactly the same way until we get to the last step. And at the last step, since this operator is going to be, this is showing greater than, but now we're using less than, less than, less than, less than, less than, less than, the division would turn into greater than. And the answer would be that it would be that the first algorithm is better whenever p is greater than 1. Well, when is probably greater than 1? Never. So therefore the answer would be that algorithm on average is never better. Because p cannot be greater than 1. And the last question I can ask is, when do these algorithms perform the same? And so that operator, instead of being greater than or less than, I could just arbitrarily set it to equal. And if I have equal, the nice thing about that, when you divide by a negative value, the equality stays an equality. And so therefore the answer would be 1 are they equal? And the answer would be when p is equal to 1 or equal to 1. So when the element is definitely in the array, the algorithms on average behave the same. Okay? So that's very important. So on a test situation or in a homework situation, what I will do is I will give you an algorithm like this, and I will ask you, here's the result of an average analysis of this algorithm. Here's the algebraic result. Here's the other one. Tell me when this one is better than this one. So what you're going to do is you're going to take this one less than that one, and you're going to simplify it as simple as you can. In some cases, p, if p is a probability, it will stay. In some cases, p is going to disappear. Make it as simple as you can so that it makes some logical sense. So you can make a reasonable interpretation of that. Okay? So some cases, I can give you the algorithms and you have to give me the algebra for the average complexity. In other cases, I may just give you the results and say, okay, tell me when this is better. Okay? All right, good. Any questions about that? So this is important because we do want to be able to compare algorithms and performance of those algorithms. Okay, so now what we're going to do is we're going to do an analysis of trying to find the complexity of algorithms, and specifically we're going to start with recursive algorithms. So what are recursive algorithms? What's the recursion mean? What does recursion mean? Not a loop, that's exactly the opposite of what it doesn't mean. Recursion means that a function or a procedure or something like that, or a method, actually invokes itself. Okay? So, an example of something like that would be the factorial function. And so we see that type of thing lots and lots. The factorial function basically says the factorial of 5 is 5 times 4 times 3 times 2 times 1. But the factorial of 6 is 6 times 5 times 4 times 3 times 1. So therefore the factorial of 6 is equal to 6 times the factorial of 5. So to give you the value of factorial of n, I will say that's n times the factorial of n minus 1. So you're answering the question of the factorial by invoking another factorial. That's a recursive answer. But eventually that recursion has to simplify. If the factorial of 6 is 6 times factorial of 5, and the factorial of 5 is 5 times the factorial of 4, tick, 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 etc. Factorial of 2 is 2 times factorial of 1. 1 is 1 times the factorial of 0. The factorial of 0 is 1. By definition, the recursion has to stop. So when you have a recursive function, that function must reduce the input of the recursion and drive it towards what we call the base case, when we can simply give an answer. What's the factorial of 0? 1. What's the factorial of 1? 1 times the factorial of 0. What's the factorial of 0? 1. Okay, so it's 1 times 1. That's 1. Does that make sense? So that's a recursive function. And this code shows you the recursive function. If, and again, I'm not giving you the precondition and the postcondition of these functions, but you understand what should be the precondition of in n. What should be the precondition for n? It should be an integer 0 or higher. Another way of putting that, it should be a non-negative integer. Non-negative integer. Then we're good. That's the and then what's the postcondition? The postcondition is the function returns the factorial of n. If you give me a negative integer, all bets are off. The postcondition does not guarantee anything. Horrible things will happen. Computers will blow up. Stacks will overflow. Dinner will burn. I don't know, something like that. Anyway, so that's the function. So the function says if n coming in is 0, just return 1. That's the base case. Else return n, the parameter, times the recursive factorial of n minus 1. So what we're going to do is we're going to try to find out what is the complexity of this algorithm. It's a recursive algorithm. What's the complexity? Well, the complexity, we can say t of n is equal to 1 plus t of n minus 1. I'll explain that in a second. And t of 0 is equal to 1. T of 0 means that 0 actually comes in as a parameter, and because n equal to 0 is true, we return 1. We will count that return as a single statement. So if you give me factorial of 0, I will need to execute one statement, and I'll return correctly the value 1 to you. But if you give me a value that's higher than 0, like 1, 2, 3, 4, 5, etc., then this condition will be false. I will return to you the product of n times factorial of n minus 1. This is a recursion, and this is the t of n minus 1. This star, which is the multiplication, is the operation I have to do here. That's the operation I have to do. So I will do one operation, which is the multiplication, and I will add to it the cost of recursing, trying to get the next simplification of the next value. Okay, does that make sense? So that's the recursive breakdown. Now let me show you one thing how I'm going to be counting recursions. So let's say I have this hand right here is an outside call. I want factorial of 3. So factorial of 3, this is the code. So 3 this is the code. The code calls the function. So I'm just calling factorial of 3. I have no idea factorial is recursive. I don't care. So therefore, 3 is called, and it goes into the function. I'm now executing the factorial code. But before I finish the factorial code, I call another version of the factorial code. And before I finish that, I call another one, possibly another one. Eventually, I finish. when the call sends in the 3 as a parameter, we say that we are executing factorial at level 0. And the reason it's level 0 is because it's 0 recursion. That means that this outside call is just calling ordinary function. But when factorial calls itself with a 2, now we are at factorial level, recursive level 1. That means we are now, recursive level 1 means we were called from factorial itself. And when that 2 invokes another recursion with a 1 coming in, that's recursive level 2. And then when that 1 calls factorial with a 0, that's factorial level 3. When factorial level 3 returns, it returns exactly to the last place it was at factorial level 2. When factorial level 2 returns, it goes back to 1, and when 1 returns, it goes back to the call. So we count recursions starting with 0 when it's the outside call, and then as we recurse, then it's 1, 2, 3, etc. Eventually, we drive these recursions towards the base case, and they just keep unwinding backwards until we go back to level 0. Level 0 returns to the call. Okay? All right, so this is a technique called repeated substitution. So notice that we have T of n is equal to T of n minus 1 plus 1. This is called the recurrence. We want to find out what is T of n in what I call the closed form. The closed form. The closed form means that the T of n cannot have another T on the right side of it. So the way we're going to do it is we're going to say T of n is equal to T of n minus 1 plus 1. T of n minus 1, all I need to do is plug in n minus 1 into n as a substitution, and therefore if I plug in n minus 1 for n, I get T of n minus 1 is equal to T of n minus 1 minus 1, which is minus 2, plus 1. And if I want to find out what is T of n minus 2, I plug in n minus 2 as a substitution for n. And therefore I get T of n minus 2 minus 1, which is T of n minus 3, plus 1. I can just continue doing that over and over again. Of course, we don't want to keep doing this over and over again because we'll never finish. So what we're going to try to do is we're going to try to be clever about it. And what we're going to do in this case is we're going to say T of n is equal to T of n minus 1 plus 1. And now what I'm going to do is I'm going to substitute what T of n minus 1 means. So I replace this circle in here with this bracket, because this bracket is the value of T of n minus 1. So that's a substitution. Once I do that substitution, notice that I'm going to look at T of n minus 2, and I'm going to say, hey, I have a value for that, and T of minus 2, n minus 2 is T of n minus 3 plus 1. I put on the inner bracket the value of T of n minus 2. I have done the substitution 3 times. From T of n to T of n minus 1, expanded twice, expanded 3 times. When I do this 3 times, it's usually enough to try to see the pattern. And the pattern is, if you simplify this expression, you will get T of n minus 3 plus 1 plus 1 plus 1 plus 3. But I made 3 substitutions. So therefore, I assume that if I make 4 substitutions, it's going to be T of n minus 4 plus 4. Or if I make, generally speaking, I substitutions, I'll get T of n minus I plus I. So if I just keep substituting, I'm going to get this pattern here. So now what I can do, since I can be any number, I can do this 1 time, 2 times, 3 times, 4 times, 5 times, I times. I can do it n times. I can do it n minus 1 times. I can do it n plus 1 times. I can do it whatever I want. I will plug into the value of I whatever I need to make the inside of these parentheses match the base case. And the base case is 0. And the only way n minus I is equal to 0 is if I is equal to n. So therefore what I'm going to do is I'm going to substitute I with n, and therefore it's going to give me T of n is going to equal to T of n minus n, T of 0, plus n. But T of 0 is 1. So therefore my recursion has a cost of n plus 1, and that's the closed form. Because now we do not have any T of n's, or any T on the right side. Closed form, get rid of the recursion. Sometimes recursion in mathematics is called a recurrence. It's the same thing. Recurrence. Okay? All right, let's see what we can do. So let's go to another very interesting example. This is one of my favorite problems. How many of you are familiar with this famous problem called the Towers of Hanoi? Okay, it's a very famous problem in computer science. And it's not a very practical algorithm, but it's extremely typical of possible algorithms that you can have that will have the exact same complexity. Okay, so Towers of Hanoi goes like this. I guess I'll show it to you. It's best if you look directly at me, because I don't have enough board space to really do it. So imagine that we have 1, 2, 3 bases, and they have like a little, I don't know, stick that goes up there. And our job, and we'll call this A, we'll call this B, we'll call this C. And our job is to move the disks that are on these sticks from place to place. Specifically, we're trying to move all of them, typically from A to C. Now, if there's only one of them, guess what we can do? We pick it up from A, and put it on C. Now, if we have 2 of them, the rules are such that a bigger disk can never be on top of a smaller one. So if I have 2 disks, that means A must contain a bigger disk, and on top of it is a smaller disk. Okay? If I have 3 initially, then I'm going to have biggest, middle, smaller. If I have 4, it's going to be biggest, smaller, smaller, smallest. If I have 1,000, you get the idea. It's going to be like a pyramid shape. Now, the rules of solving this Towers of Hanoi is that we can only move 1 disk at a time. Okay? And we can never, ever have a bigger disk on top of a smaller disk. So watch very carefully how we're going to solve this problem. So with 1, 2, 3 of them, and only 1 disk, you just go up, and you're done. 1 move. But if I have 2 of them starting at A, and I want to go and put it onto C, I have to take the smaller disk, which is on top. It's the only one I have access to. And I can only lift 1 disk at a time. I will put the smaller one onto B. Then I will take the biggest one, the bigger one, and put it onto C. And to complete, I'm going to now move the smaller one from B to C. So I've solved it for 2. But let's see what I really solved. What I really solved is that I can start at any particular peg, I'll call them pegs, for any particular peg, and move it to any other pegs, any of the other 2 pegs. If I have 2 disks, I can do this in how many moves?
3.
Little, big, and little follows. 3 moves. Now, would you agree that I can equally easily move from A to B those same 2 pegs, the same 2 disks? Sure. Then I can move the little guy on C, the big one on B, and this goes onto B. So moving it onto B or C is the same. Sequence of steps might be slightly different, but the same number of steps. So what we found is that we can move 2 disks in 3 steps. So now I want to see whether we can move 3 disks. So I'm going to argue recursively. So I have 3 disks on A. 1, 2, 3. I know that I can move 2 disks from one location into any other location in 3 moves. So therefore, I can move these 2 top disks onto B in 3 moves. How am I going to do it? Little guy goes to C, middle guy goes to B, little guy goes on top of B. That's the 3 moves. So I can do it. What happens then? The big guy goes from A to C, and now it's the biggest, so it doesn't have any problems with being on top of anything. It's just right there. Now all we need to do is move the 2 disks from B to A. But I know I can move 2 disks from a starting point to any other location in 3 moves. So therefore, the total number of moves is going to be 7. So now the next argument is going to move 4 disks. 4 disks. I will take the top 3 and I will move them through the same technique. 7 moves now, and they'll end up in B. I'll move the big one, and then 7 more moves. They'll end up on C. Did I convince you that it can be done? I hope so. Okay, so it can be done. What's going on with the number of moves? Well, we went from 1 to 3 to 7 to 15. We always doubled the previous 1 plus 1. So 7 doubled plus 1 is 15, 31, 63, 127, etc. Okay, so that seems to be the complexity of Towers of Hanoi. Let's take a look how we can solve it. So this is the pseudocode. This is the pseudocode for this algorithm. And so therefore, this only happens if n is greater than 0. That means if n is equal to 0, there are, notice if this, you can take one recursion, one simple operation, which is a move, and one recursion. So if I have n disks, I will move n minus 1 from the A to the auxiliary, which is the B. I will make one move of the big one, and then I will move the n minus 1 disks from the auxiliary onto the 2. That's the recursive algorithm, and it's actually, believe it or not, it's as simple as that, or as complex as that. I don't know, whichever one you want to think of. But let's look at the complexity of it. T, the complexity of 0 is 0, because if n is greater than 0, we do stuff. If it's not greater than 0, we skip the code. Skipping the code means 0 instructions. So we get T of 0 is equal to 0. But T of n, whenever n is greater than 0, it's going to be T of n minus 1. That's the recursive cost of Hanoi of n is Hanoi of n minus 1. That's T of n minus 1. Then I will do one move, which is the 1. That's the operation. And then I have another T of n minus 1, because I have to now move those n minus 1 disks on top of the big one. Right? So that's the recursion. Now, of course, I can say, hey, this is happening once and twice, so it's really 2T of n minus 1. So I can simplify my recurrence like that. Any questions so far? So now I will do repeated substitution. It's going to look like this. T of n is equal to 2T of n minus 1 plus 1. Now T of n minus 1 I will solve by substituting n minus 1 for n. So I'll get n minus 1 minus 1, which is n minus 2, plus 1. You can see that I can do the same thing for T of n minus 2 and T of n minus 3. So let's do this 3 times and see if we can make a pattern like we did last time. Okay, so what we're going to do is we'll do this 3 times. So what we have is initially, this is the first substitution. Now look very carefully. Notice that T of n minus 1 has 2 terms. T of n minus 1. So I take the stuff in the bracket. I take the stuff in T of n minus 1 and I put everything in the bracket. So everything in the bracket is the value of T of n minus 1. Once I do that, I'm going to very carefully put a substitution in between the 2 and the T and after this parentheses. So I'll put a bracket after this 2 right here, and I'll close the bracket here before the plus 1. And so I've done it 3 times. This is not as simple as before because we have some multiplications to do. So you have to do this very carefully, okay? And when you do this carefully, you'll see that after the 3 substitutions, the first thing I'm going to do is I'm going to take this 2, and I'm going to distribute this 2 across this bracket. So it's going to be 2 times 2 is 2 squared. 2 times 1 is 2 to the 1. And then plus 1, I just wrote 2 to the 0. So now I have to distribute this outer 2. This outer 2, when I get 2 to the 3rd, plus 2 to the 2nd, plus 2 to the 1st, and then finally I get plus 1, I'm going to write that as 2 to the 0. So now I have a sequence of numbers, and notice that it's going to be basically 2 to the 3rd power times T of n minus 3 plus 2 squared plus 2 to the 1st plus 2 to the 0. Now, how many substitutions did I do? I did 3. I substituted once here, once here, once here, then I simplified. 3 substitutions. So therefore, I'm going to now hypothesize if I do this I times, instead of 3, I'm going to get I. Instead of 3, I'm going to get I. And instead of 2 to the 2nd, I'm going to get 2 to the I minus 1. Because 3 is I. So therefore, since this is 2, that's going to be less than I. So I minus 1, all the way down to 2 to the 0. So now what I'm going to do is I'm going to look at the repeated substitution that I have, and I'm going to try to simplify it. How am I going to do that? Well, I'm going to repeat it I times, and then I'm going to choose something in here that's going to make me fall back into the base case. So what would I be so that we have a base case? Well, we know T of 0 is equal to 0. So therefore, I'm going to choose I equal to n again. And when I is equal to n, I get 2 to the n times T of 0 plus 2 to the n minus 1 plus 2 to the n minus 2, and so forth until 2 to the 0. So what I have is I have the summation of 2 to the I power as I ranges from 0 up to n minus 1. Now, we're going to talk about how to solve this. Some of you may recognize this as a geometric series, which, by the way, our textbook has a nice appendix, shows you the geometric series derivation. But the geometric series basically is going to say that the sum of the n terms of a geometric series is going to be the first term, a, minus the second term, a, times the ratio of the terms, I'll talk about later, to the number of terms, n, over 1 minus the ratio. Now let's find out what we mean by the ratio and the number of terms and all that kind of stuff. So for example, suppose, look at the summation. Summation goes from 0 to n minus 1 to the I. What's the value of the first term when this thing is, when I is 0, 2 to the 0 is? 1. So we have over here, we have 2 to the 0. Next time around, we have plus what? Summation. 2 to the 1 plus 2 to the 2. And the last one is 2 to the 2 to the n minus 1. So this is a geometric series. Why? Because the value of this is 1, and the value of this is 2, and the value of this is 4, and the next one will be 8, and the value of the last one is going to be 2 to the n minus 1. So you can see that each term is, we can derive the next term by simply taking the previous term, multiplying it by 2. So therefore, in this particular series that we're adding, the first term, a, is equal to 1. The ratio is what you multiply each term to produce the next term. So what's the ratio? So ratio is equal to 2. And the number of terms is the number of terms. Since the first index is 0, and we're going to go from 0 to 1 to n minus 1, if you just add these numbers together, you'll get n minus 1 terms. But then you've got to add the last one, therefore the number of terms is, in this case, is equal to n. So therefore, what we're going to do is we are going to use this formula for the geometric series, which is going to be 1 minus 1 times 2 to the n over 1 minus the ratio 2. So what we have is 1 minus 2 to the n over negative 1. And when I multiply top and bottom by negative 1, I get 2 to the n minus 1. That is the complexity of Taussig-Frénois. So therefore, if we have 10 disks, the number of operations we expect is 2 to the n, 2 to the 10 minus 1, which is what? 1,023, because 2 to the 10th is 1,024. If we have 20 of them, we will have a meg, 2 to the 20 is a meg, minus 1. If we have 30 of them, it'll be a gig minus 1, which is